All right, so we said before that we had two groups of people working on two different problems. Number one, how do I find the slope of a tangent line? They were essentially discovering derivatives. But another group of people working on how do I find distance traveled? Oh, I can find it by finding area under a velocity curve. And here's a new notation that I'm going to make up for it. That's called the integral. They were working on evaluating integrals. It turns out they discovered somewhere along the line that the two problems were totally related. And how are they related? Well, here's the big secret, is that derivatives and integrals turned out to be inverse operations. That means derivatives undo integrals and integrals can undo derivatives. So this understanding of the relationship between derivatives and integrals is summarized by what we call the fundamental theorem of calculus. And as you guessed from its name, it's going to be key to your understanding of calculus, key to your success on the AP test. The fundamental theorem of calculus has two parts. Some people say that they can tell which part is part 1 and which part is part 2, but then another book has them flipped. So I don't specify which one is part 1 or part 2, but you need to know two parts of the fundamental theorem of calculus. They are both critical. So we're going to start with this part, which essentially says that you can take the derivative of an integral. The derivative of the integral will undo each other and leave behind whatever's left in whatever was started inside the integral. So just for discussion, if I said square roots and squaring undo each other, so that radical and that 2 there are going to cancel each other out and leave behind the only other thing that was left was this 5. So we're going to see that derivatives and integrals do that same thing. There's some rules though. It's not that it works in every case. So there have to be a couple of guidelines we make sure we follow. Let's see if I can, there we go. Okay, so remember this operator ddx means take the derivative of. So this means I'm going to take the derivative of the definite integral from a to x of the function f of t dt. And the answer is going to be f of x. So watch what has to be true. You have to be taking the derivative of an integral for this to apply. It has to be a definite integral, and the upper limit on the definite integral has to be an exact match for the variable that you're taking the derivative with respect to. And the lower limit of your integral has to be a constant. Could be pi, could be e, could be -1/2, could be 3.21798. Has to be a constant, but any constant. All right, so if those things are true, then this operator which takes the derivative and this operator which integrates, they cancel each other out and leave behind the function that was here, except that instead of being f of t, or whatever function it was originally, all the t's convert into x's. Whatever the old input variable was is going to change to convert to whatever that upper limit variable was, to whatever the variable is that you're taking the derivative with respect to. So let's do an example. So if I apply the fundamental theorem of calculus, watch this. This lower limit is an x. Sorry, this derivative, the variable that I'm taking the derivative with respect to is x, and the upper limit is x. So those had to match. That works. I'm taking the derivative of an integral. That was supposed to be the first step I checked. Third thing, the lower limit has to be a constant. Well, negative pi is a constant. So all three of my criteria are met. If I just straight up jump to using the fundamental theorem of calculus, the fundamental theorem of calculus says that my answer is going to be whatever that function was, but instead of being a function of t, it's going to be a function of x. Okay, so fundamental theorem says my answer is supposed to be cosine of x. So just notice that I could actually do this problem without knowing the fundamental theorem of calculus. We're going to do it the long way, and we're going to prove to ourselves that our answer is actually cosine of x. So to do that, remember what we did in class today. I asked you to evaluate a definite integral using an antiderivative. So we might ask ourselves, here's what I'm going to do. I'm going to try to evaluate that integral, then take the derivative, see if I get cosine x. So So I'm going to start with what I did in class today. I'm going to figure out an antiderivative for cosine. And antiderivative, I'm going to call it capital F of t, is going to be sine of t. Just notice this new notation. I've referred to this notation that's going to come up. You're going to find it's very much more convenient than what we did in class today. So notice that I've decided that sine of t is my antiderivative. This is a notation I can use to say I'm going to evaluate sine of t from a to b. So that's going to be f of b minus f of a. In this case, notice the limits look exactly the same as they looked up here. When I read this, I would say I'm going to evaluate sine of t from negative pi to x. And that means exactly what we did in class today, which is sine evaluated at the top limit minus sine evaluated at the bottom limit. So watch what happens. Sine of x turns into this, minus sine of negative pi turns into this. But look what happens next. I've been waiting, this derivative operator has been waiting around to take its turn. Now it's going to be time to take the derivative of all this stuff. I'm going to take the derivative of sine of x, which I copied down here. When I take the derivative of the sine of negative pi, it doesn't matter if you can't think of what the sine of negative pi is. We know sine of negative pi is going to be some number. When I take its derivative, the derivative is going to be 0. So I'm going to get my final answer, derivative with respect to x of sine of x, which is cosine x. That's what I knew the answer was all along. So you can see here we sort of summarize that same example. If the variable that we're taking the derivative with respect to is a perfect match for the upper limit, and we're taking the derivative of an integral, and the lower limit is a constant, we can simply use that first fundamental theorem of calculus to hop right to the answer. All right, so try this one. I want to take the derivative with respect to x of the integral from 0 to x of 1 over the quantity 1 plus t squared and times dt. I'm taking the derivative of an integral. That x here matches my upper limit. The lower limit of integration is a constant. The derivative is going to undo the integral and give me the same function I had as my integrand, except with all the t's turned into x's. So 1 over 1 plus x squared. This example, I think I use r's on my paper, but if I want to take the derivative with respect to x of the integral from 0 to x squared of cosine d dt, my 3 rules aren't met. I am taking the derivative of an integral, and my lower limit is a constant, but my upper limit is no longer a perfect match for that variable that I'm taking the derivative with respect to. So I have to use the chain rule. Everything else works as planned. My cosine of t is going to transfer into a new function, which is exactly the same, but all the t's are going to be replaced with x squareds. That's how I get cosine of x squared. But then I'm going to have to multiply by that derivative of the upper limit. And that's if you want to get into the proof of it, it's the use of the chain rule. So that's going to be times the derivative with respect to x of x squared. So my final answer, cosine of x squared times 2x. So notice 2 important things. That upper limit replaces the variable. So this doesn't just turn into cosine of x, it turns into cosine of, what's that upper limit? X squared. And then I have to multiply by the 2x. That's the chain rule. On your handout, I use slightly more exciting variable names, but then when I tried to change my PowerPoint file to go with it, my equations broke. So I have slightly less interesting variable names, but this is the same kind of problem. If I want to take the derivative of this integral, I'm definitely taking the derivative of an integral, so that first step is met, but now I don't have my upper limit matching, I don't have my lower limit as a constant. In fact, my limits, I really wish I could switch them. If I could switch the limits, they'd be in the right place. Well, remember, I can switch my limits. I'm just going to need to take the opposite of the value of my integral. That opposite does factor out into the front, so I'm going to have the opposite of the derivative with respect to x of the integral from 5 to x of 3t sine t. So now here's my negative stays out front. I have a lower limit that's a constant now, an upper limit that's a perfect match for my variable. I'm going to replace all my t's with x's to get my final answer. Here's one last example I can answer using the fundamental theorem of calculus, this part of the fundamental theorem of calculus. What if I want to take the derivative of an integral, but neither limit is a constant? I can use one of those properties that I learned in 5.3 and split the integral up into two parts. Pick any constant you want. In this problem, I happen to pick 0. You can pick any constant you want. You're going to get the same result. And you don't even have to know or have any kind of promise that 0 is between 2x and x squared. This works with any number. You can split up an integral by picking some number and saying it's between those limits. There's no problem. So I'm going to think of that as the integral from 0, as the integral from 2x, there's my pen, from 2x to 0 plus the integral from 0 to x squared. Now I can take the derivative. Notice I'm just taking the derivative of sum now. I'm going to add together derivatives. So breaking that integral up hasn't affected my ability to take the derivative. And look at my second integral now. I wish I could switch the limits, so I do, and I'm just going to change from addition to adding the opposite, which is the same as subtraction. So now when I, now I can take the derivative of each of those parts. Those derivatives are going to undo the integral. In my first integral, my upper limit is not a perfect match for my variable. It's a function of my variable. So notice how this t is replaced by x squared. So I have 1 over 2 plus e to the x squared. This is times 2x is the chain rule because my upper limit is not an exact match. It's a function of the variable. This is the subtraction sign. Here, the integral from 0 to 2x, my lower limit is a constant. That's good. But I have this problem where my upper limit is not just an x. It's a function of x. So notice my t is replaced in this case with 2x, that upper limit, and I've here multiplied by 2. That's using the chain rule. And here I've simplified, but notice on the free response section you would have no obligation to simplify. With that being said, I've never seen a question like this in the free response. It's always been a multiple choice. Interesting.